Yeah, so let us start. Yeah, one more thing, one more correction from our previous lecture, not last class, but long back, like few classes back, while we were studying convex set in ellipsoid. Okay, so here we said we saw an ellipsoid equation of an ellipsoid. Then I said that the axis will be having length of 1 by root lambda i's, which is the eigenvalues of p. But the thing is, if you are like here, I consider lambda i's are the eigenvalues of p, not p inverse. Okay, in that case, this has to be not 1 by, it has to be root lambda. Okay. Okay, so please make this correction. So because lambda is the eigenvalue associated with the eigenvalue of the matrix P, not P inverse. So like then the axis, length of the axis of this ellipsoid will be root lambda, not 1 by. Okay, so let's start today's lecture, a new topic, convex problem. So we saw what is a convex problem at the first class itself, which has a an objective function, which we will minimize or maximize, right? And then we have certain constraints. Then we said that at what uh, condition we can call this problem as a convex problem. So what was the condition? The objective function has to be convex, right? And the set associated with the constraints, that set has to be convex, right? Now with this definition in hand, we uh, move to further details of convex optimization problem. Here we will see more standard definition of convexity of a problem, and then this is a very important part of our lecture series, where in this course uh, we will see different. We will first familiarize with what is a convex problem in a standard form, and then we will see different classes of convex problem, like uh, a linear optimization problem, quadratic problem, like semi-definite problem, and these are different classes of optimization problems. So in your research, if you have an optimization problem, and then you form, after this lecture you will be knowing what are the standard form. Now if you can link your problem to one of the standard form, then it is done. You can easily solve that, because there are a lot of solvers which can take care of that. For example, your optimization problem of your research is a, you happen to know that it's a quadratic optimization problem, then like you can have many, you can like easily search for the solvers for that. You don't need to design an algorithm unless it's very required. It is required. If it's a normal or if it's a like a simple quadratic optimization problem, you can just use the one any solvers which are available, or even some default MATLAB command can solve this quadratic optimization problem. So in this lecture, we will see what are those standard classes of optimization problem. Yeah, so let's start. An optimization problem in standard form. We already saw a part of it. So we have an optimization problem, which is we minimize an objective function f0x subject to certain uh, inequality constraints. And now I'm saying that let's consider an equality constraint. Okay, so previously I think we were just taking a form like this, right? But now we are adding one more constraint, which is an equality constraint. So actually this comes from this. So any equality constraint, for example, if I say something like h of x, h1 of x equal to 0, this I can equivalently write as h1x is less than or equal to 0, h1x is greater than or equal to 0, right? This means h1x equal to, sorry, 0, right? This means h1x is equal to 0. So there is nothing new. We just add that equality constraint here. Okay, why? Because later we see that based on this structure of the problem, like we have objective function, inequality constraint, and equality constraint. So then what are the requirements of inequality constraints, and what are the requirements of equality constraint for the problem to be convex? And then we will develop our further theory based on this standard form. So remember, now we have an objective function, inequality constraint, and equality constraint. Okay. Also, yeah. So here we use the index 0, f0x. Okay, f0x means objective function, but we have also f1, f2, like these functions like this. So these are the constraints, functions in the constraints here. Okay, that's why I equal to 1 to m. Okay, f1. So and this is the first guy, f0 is our objective function. This is the convention we are following here. Okay. So the moment at any place in the lecture, if you say f0 x, that means it's an objective function by default. If you say f1x, that is from a constraint region. Yeah. Yeah. So we have the optimization variable x, right? So we are minimizing this over x, and objective function f0, inequality constraints fi, and equality constraints hi. Okay. Hi is a function, and when hix equal to 0, that will be a constraint, right? So that is an equality constraint. Now we'll see, before moving into standard form, we will see what is an optimal point, what is a local minima, what are some conditions for optimality. So these kinds of basic concepts are very necessary before we move to the uh, standard form, or before we study the classes of optimization problem. Yeah, so let's see what is an optimal value. Okay, so what is an optimal value? Like we already know now, right? For example, we have a function like this. So optimal value will be this point, right? The global minimum, right? So optimal means it should be global minimum, optimal value. But if it's not a global optimum, we also have other kinds of optimum which we call as local minimum, right? So for example, here this is a local minimum, but when you say optimal value of the problem, that means global minimum by default. Yeah, so how do we define an optimal value? So p star, we denote optimal value of our problem as p star, which is defined as infimum of f0x, right? So it's not the, remember, it's not the argument, it is a value. So we have some particular x opt which minimize this function, okay? And this value is p star, okay? So p star is infimum value of f0x over x, right? Such that these constraints are satisfied. So infimum value of f0x such that the inequality constraints are satisfied and equality constraints are satisfied. This is called an optimum value. Then there can be many scenarios. One is uh, uh, one special case is P star is infinity. So what does that mean? See, we are minimizing a problem. Then we say that, okay, the minimum value, my minimization is, or the minimum value of the function is infinity. What does that mean? So that means there is no solution, right? Mm-hmm. Right. So what does that mean? So I have a problem. I am asked to minimize. Now I am saying that, okay, I cannot find a minimum value, or I cannot even, what is optimum minimum value infinity means I cannot even try solving this problem. I cannot even find two feasible region, two feasible point x1 and x2, and say that, okay, x1 is less than x2. This is not even happening. Just at the infinity level, I'm saying that the minimum is infinity. There is no other points. Okay, so that means the problem is infeasible. I cannot find any value x that satisfy these constraints. So when a point x satisfy these constraints, that is our inequality and equality constraints, then we can say that we call x as a feasible point. Okay, right? So that's in the feasible region. Means basically that falls in our constraint set and in the domains of our functions. We'll see this. What is a feasible region? But when there is no feasible points, in that case, I just assume this convention. So this is a very standard convention where p star equal to infinity. That means there is no feasible point. Yeah. So like this comes from a standard convention where we say that the infimum of a null set. What will be the infimum of a null set? There is nothing. Right? So we say that it's infinity. We cannot find a minimum value. Okay. So just let's keep it as infinity. Okay. That means we don't have anything to minimize. Okay, like just say that that's plus infinity. So this is a standard convention. Okay, it's a convention. Yeah, so that is when the problem is infeasible. Now the problem is another case is the problem is unbounded below. So we are minimizing a function and it has no lower bound. It keeps on decreasing. Okay, for example, yeah, here we have minus log x. So if you minimize this, what will happen? What is the minimum value? So this is decreasing like this, right? So as you keep moving to the right side, means more higher values of x, you will get more smaller values of the function, right? So that means it is not unbounded below. So the problem is unbounded below. In that case, our optimum value will be minus infinity. One other important point is here we
you said not unbounded below. It should be unbounded below. Right?
I said not unbounded. So not bounded below.
Yeah, not bounded below.
Okay, sorry. Not bounded below or unbounded below. Means there is no lower bound we can
then
say.
It will be minus.
Yeah. So another concept is infimum. Okay. Another point here you have to see is infimum. That means, for example, if you are let's take an example. What? Yeah, simply minimize x. Okay, and x is let's take this problem. Okay, minimize x and x has to be in this set. So what will be the p star here?
C.
No, you should see the definition of P star. That is the infimum. So it can take the lower bound. That's my point. Okay. So P star, as per our definition of the optimal point, P star is 2 here. Although x cannot take 2, but the function, what is our function here? F of x is simply x,
Right.
right? So it can take uh, this value, and the optimum value of the function of our problem is 2. But at which point this is achieved? At which point of x is x this is achieved? It cannot be achieved in this constraint side, right? Because x is not equal to, x cannot be equal to 2. So we said that the conversion is this. We say
No,
that the,
if we take the optimum value P star equal to 2, but then it's not following the constraint, right? If you
yes,
have,
that's my point.
Yeah.
So as per our definition of optimum value, how are you defining optimum value here? So here, it's not minimum, it is infimum. Means it can take lower bound, okay?
But
So as per our definition, optimum value of this problem is 2, but it is never achieved, okay? So this problem, no value of x can achieve this optimum value, okay? That's just a convention, okay? So we say that when you have this problem, we say that, okay, I know that this is the optimum value. 2 is the optimum value of this problem, but this cannot be achieved. That's it. Okay. I just want you to know that, yeah, because we are using an infimum here. Yeah, so let's move on. Optimality and locally optimal points. Now, yeah, so now we will see what is a feasible uh, point. A point x or the variable x is feasible when if x belongs to domain of f0, right? Of course, f has to belong to the domain of f0. Otherwise, we cannot say that that is feasible, right? And it satisfies the constraints. Okay. So whenever x is satisfy the constraints, x if you can find an x which satisfy all your constraints and which falls in the domain of the objective function, then we can call that point as a feasible point. Okay. Now, a feasible point x is optimal if that point that point gives you the optimal value of the problem. So these are very simple things. We are just formally stating it. Okay. So a point x, for a point x to be optimal, one thing is it has to be feasible. Okay. Otherwise, we cannot find an we cannot say that x is an optimum point. So x is optimal. One thing is it is feasible. Second thing is it achieves, if you plug that x in the objective function, it achieves the optimal value. Okay. So here you cannot find any x which achieve this value. So here you cannot find any optimal point. Okay. But the optimal value of the function is this. Yeah. So here, like we know that this is achieved when x equal to 2, but then that 2 is not feasible.
Yeah, then here x is not feasible also, right?
Yeah, that's what I'm saying. X is not feasible. So the optimum value of this value is achieved. So how do you get the optimal value? From this definition of optimum value. Okay. So that value is achieved for x equal to 2. Okay. But that 2 is not in a feasible region. That 2 is not feasible. So it is even it's violating the first condition itself. X is feasible. X is not feasible here. So we can say that although the optimum value of the problem is 2, P star is 2, there is no optimal point. There is no x which achieves this. Okay.
So
this is just
whether
a
it's feasible or not, we can find the optimal value. Is it like that?
Yeah.
Okay.
that's what's happening here, right? So all such things comes because we use infimum here in the definition of optimal point. Okay. Yeah. So X is optimal if this is achieved and X is feasible. And X opt, this is a set of optimal point. Why do you say a set of optimal point? Because, for example, here, if I minimize, I will have only one X opt, right? But here it is unique. But this cannot be the case always. We may have, for example, here we may have a function like this where you have many optimal points. Okay. So in that case, we have a set. It's not a single value. We have a set of optimal points. And we call that set of optimal points as xopt. Yeah. So this is just to make you aware that there can be many optimal points in a problem. It depends on the problem, function, nature of the function, and also the constraints. Now, let's see another important concept, local optimal. So you already know what it is, but let's formally define that. So when do you say that? When do you say X is locally optimal? So here, let's take a function f of x or f of z in variable z. Okay. Now, what is the optimal point of this function? What is optimal value? The value corresponding to this, right? So this is p star, the optimal value. Okay, and it is achieved at z0. Okay, so let's say that the constraints, the feasible region is entire R. Okay, so we don't need to worry about feasible region at this example. Okay, so this is the optimal point. So this is the global minimum or global optimum. So yeah, so now there is a local optimal point here. So this point, right? So this is a local minima. Okay. Also, this point is a local maxima. Okay, but let's forget about maxima here. Let's focus on a minimization problem where we are interested in only minimas. Okay, so here we have a global minima, and here we have a local minima. So the thing is, how do you define this local minima? So what I'm saying is, okay, my original optimization problem is to minimize this function. Now I am rewriting this original optimization problem such that I am saying that around x, okay, I consider a neighborhood with a distance r on both sides. So now if I impose this constraint, okay, and then if I solve my optimization problem on this constraint, okay, and now if I have a global optimum to this point or global minima to point right here, if I can find, then that will be a local optima of the origin problem. Okay, so that's here. So this part is our original optimization problem. So I am rewriting by adding a certain constraints. I can find an R such that the distance from X, okay, a distance from a specific point X of the optimization problem. So what does this mean? I this is an optimization problem in the variable z, right, over z. So now I consider all z such that its distance from a particular x is less than r. Okay. So now I consider all z such that its distance from this particular x is less than r. That means I am considering only this region. Okay. So in this, for this new optimization problem, if I have a global optimum or an optimal point x, right? If I have a value here, then that means that is a local optima of the original problem. Okay, so basically we just say that, okay, if this is a local optima, just consider a segment, a region around it, and that should be a global optima for this.
So to have this local optimum value, it's like initially we'll be having a problem without any constraint, and then after that some constraint will come.
Yeah, so this is just a definition of local optima. Okay, so I'm not saying that in a problem you have to do this or something.
Okay.
This is
So
a way to this is a way to understand or formally define a local optima.
But if you have a problem and already the constraint have given, right? Okay, this
Yeah.
is the constraint.
Yeah.
And then what you're coming up with is like global minimum, right? Because you don't know whether local minimum is.
Yeah. Yes, I agree. But the point is, I have a function like this. Okay. And now what I'm saying is, okay, when can I say a point x is a local minima? So I can say that x is a local minima. If I consider a small neighborhood around x, then in that small neighborhood, x has to be a minima, an optimal point. Okay. So now we are not worried about the entire constraint, entire feasible region. Just construct a small feasible region around x and check whether x is a x is an optimal point in that small region. In that case, we can say that x is a local minima. Okay, so it can also be global minima also, right? So the same definition applies to local global minima also, right? If you construct a small region around a global minima, that will again a global minima of that small region. So this is the way to define, way to see, visualize I will say this is the way to visualize a local minima. You take a small region around it, then that should be the main guy in that small region. Okay. Yeah.
Then the local optimal, is it already, while defining the local optimal, we define using Euclidean function, right? So is it always has to be in Euclidean, like norm to?
Yes, I will say, yeah, because we are what we do is we there is an x. What I want is, instead of feasible region, under feasible region, I have to take a small region. So that I want in terms of distance, right? Otherwise, if you
what you think is if the function is in 3 dimensions,
Euclidean norm can be distant. In that case, this norm will be this will be a norm ball, right? So in 2D, this will be a circle. Okay, so if this is in 2D, when I say x star is a local minima, so then we have to examine a small neighborhood with radius r. Okay, in 3D, it will be a ball. Okay, in 4D,
depends on vector x.
we don't know. That will be like a norm ball in 4D. That's all. Yeah. Yes, so that's the way how do we define a global minima. So now onwards, whenever we see a global minima, whenever you see a local minima, you should be able to see that, okay, I can call this guy as a local minima because in the small neighborhood around this is the optimal point. Okay, yeah. So this concept, this definition, we use in many places, in many proofs for this local minima. Yeah, so then some example. One is 1 by x. So 1 by x in positive orthant. Yes, so what will be the optimal point of this function, of this problem? So what will be the optimal value first? What will be the optimal value? That will be 0, because you know that it will go to 0. But there is no value that achieve this, right? It will be achieved only at infinity. Okay. So there is no optimal point, but there is an optimal value, right? Next is minus log x. This is unbounded below, right? There is no bound below. So what will be the optimal value of the function? minus infinity, and optimal point, no. So optimal value is the value of the function which minimizes
And
this, and optimal
at what
point
point?
is at what point of or at what value of x this is achieved. Okay, so there is no point here. Now let's take a different function, x log x. Okay, so this is a differentiable function. You can differentiate this and see the optimal point, right? So this function is like this. So the optimal value is, you can put this to be minus 1 by e. Okay, and that is achieved at x equal to 1 by e. So here you have minus 1 by e that is achieved at x equal to 1 by e for this particular
When
function.
you define log, is it to the base 10 or exponential?
Here it's to the base. Here it is to the base is exponential. Base is e. Okay, but that doesn't matter. You can do the same thing for base 10, but the solution will be different. That's all. Okay.
But the optimal value found, right?
So just see this. Okay, differentiate it, and when you like uh, you get the solution based on the base. But usually when we say log x, we consider exponential as within. Yeah. So next is a different function, x cube minus 3x. Again, you differentiate this. This is a smooth function. You can differentiate. You differentiate, and then you find 2 points, uh, x plus 1, x equal to plus and minus 1, where uh, the derivative is equal to 0. So then we can say that what will be the optimal value of the problem? This is going to minus infinity. So that will be minus infinity. This is again not bounded. It's an unbounded problem, unbounded below. Okay. Also, in this case, this is unbounded above also. Okay? And so here you can, so this value is not achieved. But you can say that, okay, but I have a point at x equal to 1, which is a local optimum point. Okay. So this is a local minima, but in this special case, we have a local maxima also, which is here, this point. Okay. Yeah. So one thing is here we differentiate to see the optimal point only because the function uh, is a smooth function which we can differentiate. If the function is not differentiable, we cannot do this stuff. Okay. Or you are giving a, yeah, we'll see that soon. Now, yeah. Now let's see what is implicit and explicit constraint. So let's take this standard form of optimization, of an optimization problem. We have objective function and constraints here. Now, what is an explicit constraint here? It is the x which satisfy these constraints. We have certain constraints, right? Inequality and equality constraints. So all values of x uh, or these constraints which we impose on x is called explicit constraint, because we are explicitly saying that. But there is an implicit constraint here, or a hidden constraint here, which says that, okay, I am plugging x in f0, right? So x has to belong to the domain of f0, right? Otherwise there is no point, right? There can be an x which satisfy this constraint, but that doesn't belong to the domain of x, f, right? So there is a hidden constraint here. X has to belongs to the domain of f0 and all these fi's. That's why we are writing I equal to 0 to m. That means the domain you are taking intersection of, so it has to belongs to all of these domains. So that means intersection of this. Again, it has to x should belongs to the domain of hi, right? So overall, we can say that x should belongs to the domain of intersection. X should belongs to the intersection of all these domains. So these constraints are not explicit. We are not specially mentioning it, but it is there. It's a hidden constraint. So that's called implicit constraint. So for example, if you consider a problem, yeah, let's take this guy, minus log x. Just see this, minimize minus log x, okay. X, I'm saying that x is let's take this, okay. Oh, okay, I will make it like this. X is between -2 and -1. Just a toy example. Okay, this is my. I'm giving you a power. Okay. So in this case, what is the explicit constraint? X has to belong to this set.
Yeah.
But you cannot take a negative value for inside a log, right? So there is an implicit constraint which say that X has to be positive. So this is implicit constraint. This is explicit constraints here, and this is implicit constraint here. Okay. Yeah. So now there can be some problem where there are no explicit constraints. So it's a problem just like what we saw in least square problem, where there is no constraint, explicit constraint. So we will just have this part. Okay. This part will not be there. This part is not there. Okay. In that case, we will say that the problem is unconstrained. There is no constraint. But remember, there is a hidden implicit constraint associated with the domain of the objective function in that case. Here, in that case, in an unconstrained problem, we just have an objective function, right? There is no constraints here, right? So, so there will be a hidden implicit constraint associated with the domain of epsilon. Yeah. Yes. Yeah. So this is an example similar to what I say. We just take this example f0, minimize this function. Okay. So this is an unconstrained problem, right? There is no constraint given, but there is an implicit constraint. This part has to be positive. Okay. Yes. Now we see what is a feasibility problem. So now we are getting familiar with the different aspects of this. One is a feasibility problem. Feasibility problem, from the name itself, you can guess what it is, right? So actually, I'm not minimizing something, but I just find the points which are feasible. That's what feasibility problem is doing. So here it is. So here, instead of minimizing, just find x, okay, such that these constraints are satisfied. So if you have a set, let's say this is the set corresponding to this constraint. Now what I'm asking in this problem is just find the values of x which satisfy this constraint. That's all. We are not minimizing or maximizing anything. So this is called a feasibility problem. So in an equivalent way, in our standard, because here we use a strange thing, find, right? So we don't know what is that find in a problem. So let's rewrite in a form that we are familiar with. That is minimize a constant. So it can be 0 or any other constant. So when you minimize a constant, what will be the minimum value of, or when you minimize, for example, 5, what will be the value? Same, right? You cannot, like, that's constant. 5 is constant. So in a funny way, I'm writing that minimize 0 such that these constraints are satisfied. So what will happen if the constraints are feasible? Then the optimum value will be 0 itself, this value itself, right? But if the constraints are not feasible, then for an unfeasible problem, we say that the optimum value of the problem is infinite. So this is a way to rewrite the feasibility problem. These are very simple things. but we will use some of this
I
later.
can't digest minimize zero. It should be find zero, right? Find x, right?
No, the thing is, yes, you can, in our English literature, okay, we are comfortable with find x, but in a optimization problem, what we often do is minimize or maximize something, right? So I'm just bringing that find, converting that find word, and adapting that to our framework that we are familiar with. That's all. So, but minimize a constant is that it's a flat thing, right? So it will be that value. So, yeah. So now we will move to standard form of convex optimization problem. By now, you know the standard form of an optimization problem, which is this. Now we are saying at what condition we can say that this standard form is convex. Okay, standard form of convex optimization problem. Okay,
Once is this the problem of objective function log b minus a transpose x?
which one? This one.
The constraints. Because a transpose x is equal to b and
Yeah, just wait. Hold a second. Hold a second. Yeah. So I will come to that. So as of now, let's you can consider this as hx equal to what was it?
greater than
Equal to zero, right? Equal to zero. We have already inequality constraint. Okay. Before coming to the details, we are going to see that. But let's now just consider h a x equal to zero. That's okay, right? Okay, so before coming to the standard form, we have an abstract form of convex optimization problem, which we were uh, repeatedly mentioning throughout up to this class, which when we said that a convex problem, an optimization problem is convex under two conditions. One is the objective function has to be convex. Second is the constraint set has to be convex, right? So that's called abstract form, a general form of convex optimization, which says that minimize a convex objective function over a convex set. So that's a complete definition. Okay. Now we move to a standard form, which says that okay, I can write an equivalent way. I can come up with an equivalent definition which says that okay, minimize f0x subject to two set of constraints. One is two sets of constraints. One is inequality constraint and other one is equality constraint. Okay, means hix equal to 0. Now under what condition this problem is convex? One is, of course, the objective function has to be convex. Second one is the functions associated with the inequality constraint has to be convex. Okay, that means all these functions from f0, f1, f2 up to f1 has to be convex. Okay, and the third thing is we have an inequality constraint, equality constraint here, right? So that equality constraint should be affine. This h has to be an affine function. Okay, so this is the standard form. Why we are saying this? For example, if you consider an equality constraint like x square equal to 1, this is not here, h is not affine, right? H of x equal to x square here. This is not affine. Then we are saying that x can be plus or minus 1, right? Then is that convex? No, right? So yeah, so always a convex problem can be visualized as this standard form. Okay, so why we are making this complicated, right? Like we should simply say okay, minimize an objective function over a minimize a convex function over a convex set. That's a very beautiful definition. But why we are coming up with this standard form is that many of our solvers are expecting this form, right? Okay, give me the equality constraints, give me the inequality constraints. Okay, so to make it compatible with that, and also for the further development of many theories that we are uh, following, we are going to learn in this lecture. It is very convenient if you stick to this notation of convex
Okay.
problem. So which says that objective function and functions associated with the inequalities are convex, and equality constraint has to be defined using an affine function. Okay. Yeah. So my question is, now let's see some of the, yeah. So yeah, before that, so this can equivalently write as this, where everything is same. Only thing is I just replace this inequality function using a matrix AX. Okay, you can just see, right? So you have an A here and X here, right? When you multiply, you will get different vectors, different entities of A here. Yeah, right. Yeah. Yeah, anyway, you can just take a matrix and multiply. Like the point is you
But
have,
didn't A matrix will be like row matrix?
it's not not row matrix. What do you mean the row? Means
Because
just
A
row.
transpose is just something.
No, it's a complete matrix. What will be the dimension of A? We can see here. So we have uh, P such linear constraint. So yeah, so A will be, so you are anyway multiplying A with X. So this has to be P cross what is the dimension of X. I think we consider X to be in Rn. In that case, this has to be P cross Rn. P cross N. Okay. Dimension. Yeah, so this is the standard form. So now onwards, we will stick to the standard form. So whenever if you are asked to examine whether a problem is convex or not, then you just see the equality constraints, inequality constraints, and objective function, and examine whether the equality constraints are like a linear constraint, and whether this is defined like a small break here.
Yeah.
Okay, let's continue. So we saw an abstract form of defining convex problem and also the standard form. So now onwards, we'll be sticking to standard form. But there is one point I would like to say. Even if you are using a standard form, you have to be careful. There can be some scenario where the problem given to you in the direct form is actually the problem given to you is convex, but when you just blindly compare that with the standard form, it may not appear to be convex. Okay, here is one example. You have a function x1 plus x2 square, which is convex, and these two guys are uh, this is the inequality constraint and this is the equality constraint. Okay, so like for example, if you take this, so what was our requirement for the function to be convex? The equality constraint has to be defined using a linear constraint or affine constraint, right? But here we have a square, so then it looks like it is not affine. But be careful here. So yeah, let's see. And also this function is not a convex function. We can maybe plot in MATLAB and see this. So be careful here. The funny thing is, if you say this x1 by 1 plus x square, what is the denominator here? That is a positive quantity, right? 1 plus a square, right? It's a positive quantity. So what does this implies? This simply implies x1 is less than or equal to 0, right? So I can simply rewrite this inequality constraint as x1 is less than or equal to 0. Because this is equivalent for any value of x2, this will be satisfied. And next one is x1 plus x2 equal to 0. x1 plus x2 square equal to 0. At what condition a square will be 0? Yeah, that has to be, this will be 0 only if x1 plus x2 equal to 0, right? Now see this. This is standard form. Objective function is convex. Inequality function is also convex. And we have a linear equality constraint, right? So this is convex now. So be careful here. So this is convex, not convex in the standard form, but indirectly this is convex in abstract form. Okay. So that's why it's written not a convex problem according to our definition. Okay. But these are like equivalent problems. So when you have a problem which you know that, or which is a convex problem and which has a strange form, it is possible that it can be converted into the standard form problem where we can have these beautiful things like inequalities are defined by a convex function and equality with unaffine function. This is possible. Yeah, now we move to some of the local and global optima with respect to a convex function. So now we already said this many times before. What is the beauty of a convex problem? Why we are so interested in convex problem? Because
If it is convex, then we can minimize, we can solve.
That is not a, if it's that's not a beauty of that. We global minimum can be for non-convex problems also, right? You have a problem like, you have a function like this can also have global minimum. So why this is important, the convex problems. So I think I said this one, but this is a bit complicated to arrange the lecture at this way, because if we actually we should have start our lecture with this proof, okay, and say why convex problems are important. But then this proof recurs some of the things that we learned later. So that only at this point we are introducing this proof, but this is the core of convex. Why we are so keen on convex optimization problem. The thing is, for convex optimization problem, any local optimum point is a global optimum point. So there can be only one optimal point, right? So you have a problem. You don't know, like for example, if I draw this function, you know that this is a convex function. But in real life, you will have a function which is in a higher dimension. You don't know the shape or something, but somehow you prove that you get a local minimum of that. Okay. Then if the function is convex, you can guarantee that that will be global minimum. That's the beauty of this. Okay. So somewhere in your function, you found a point that is a local minima. How do you define a local minima? You take a small neighborhood around that point and check whether that is an optimal point in that small neighborhood. Okay. So it's like what to say, you have a large field to search, okay, but you found a point where in a small neighborhood that is an optimal point. Then you can confidently say that, okay, although I examined this in a small neighborhood and found that this is a local minima, since my entire function, since my original function is convex, I can confidently say that this is the global minima of the problem. That's the beauty of this. That's why we are so interested in convex optimization.
What you said, you also said same, right?
Yeah, like
you said that
all convex function has global minimum.
that is true, but that is not the
Non-convex function has also
global minimum, right? Yeah. So yeah, that's the point here. Any local optimal point will be a globally optimal point. So how do you prove this? Proof is simple. So I just draw something for you to visualize. So let's take this function. So in the proof we use two properties. One is convexity of the objective function, and the other thing is convexity associated with the constraint set. So these two things are part of the proof. That's why we that's the property of a convex problem, right? Both has to be convex. So we will use both these ideas. So let's take this function of x here, okay? So and I'm saying that x is a local minimum, okay? I don't know what is the function in this part. Let's say that, and let's say there is an other point which is which is taking a value less than this f0x, less than the local minimum value. Okay, so at this point we know that this is not possible, right? If the function is convex, so if it is like this, then it has to go like this. It cannot be like this, right? But let's say that we are blind here, we don't know that, and let's assume that such point exists. Now in this proof we are going to see that this is not possible. You got it? I found a global minimum. Sorry, I found a local minima. Then no point can be lower than this point. That's a problem. So the proof is simple. Like graphically, I can show this. So yeah. So how do we say that? So I have a function. I have a point y where I assume that it takes value f0 y takes value less than f0 x. Okay. Now I am. So what is a local minima? How do you define a local minima? You take a small neighborhood. X is a local minima. Uh, if you take a small neighborhood, and in that neighborhood x has to be the optimum point, right? So in this neighborhood x is the optimum point. That you can say. So it's not small. It is like you can find a neighborhood with a radius r where it is possible that you can find a neighborhood with a radius r where the point is optimum. Okay, so this is the region with radius r. Now what I'm doing is, okay, let's, this is another point where we have a lower function value. So if you draw this point, a line between 2 points on the convex function, so we know that the graph should, the function value should lies below this line, right? That's the basic definition of convexity, right? Jensen's inequality. So we use the first definition. Okay. Now next is the convexity of the feasible region. So what I'm saying is I have 2 points x and y which are feasible. Okay. Now any points in between x and y, the line segment, any points between the line segment uh, x and y is also feasible, right? This is a convex set. By definition of convex set, this also lies in the feasible region. So now the thing is, so there I use the convexity associated with the constraint set. Now the point is, so I can pick any point here, which is feasible, and so of course I can pick an z, which is within this neighborhood. Okay, so that means, so when you pick z within this neighborhood, okay, that value has to be greater than f0x, right? Because we assume that this is a local minima. So in this neighborhood, f0x has to take a value. Uh, f0x is the optimal point, so f0x should be, of course, greater than f0z, right? Is it clear?
Yeah.
So this is the local minima here. So any point near will be having a value greater than that. That's what I'm saying here. So that is one point. But from the convexity, definition of convexity, this point should lies below f0x, because f0x is higher and we assume that a lower value of f0y exists. Okay, so then the function should be like this, and then this point has to be less than or equal to 0, so which violates this condition. That's the essence of proof.
One doubt, like, does it violate Jensen inequality at the cost?
It is not violating the Jensen's inequality.
I mean, if you draw a line between those two.
Yeah. So what I'm saying is, you assume Jensen inequality, that's the flaw of the proof. You assume Jensen inequality, that is the inequality associated with the objective function, and then you also assume the convexity of the feasible region. With both these assumptions, this is not possible. If one is a local minimum, you cannot find another value which is less than that.
But when taking Jensen inequality alone, drawing a line straight, then it falls under convex.
Yes,
Okay.
because we assume here this is a proof for a convex function, right? That's why we took the Jensen inequality for that, right? So that's why I since I assume f0y, so this has to be like this. Okay. Yeah. So now here is a formal proof. So how do you define an optimal point? F0 x equal to, now you can read this in detail, which follows the same argument that I said. Yeah, anyway. So what is an locally optimal point? It is the z which minimize f0 z such that z is feasible and in a neighborhood of x, we have to do this search, right? So that is a definition of local optimal point, x is local optimal. Now what I do is I construct, I pick a new point z. So I know that x and y are feasible. What is x and y? X is the local optimal point, and I'm saying that there is a y such that f of y takes the value less than x. This part. Okay. Now since I know that x and y are feasible, so I can pick a point z as a convex combination of x and y. That also will be feasible, right? By the definition of convexity of feasible region. And now what I do is I pick an example. I pick a theta value which is r by 2 into norm of y minus x2. Okay. So, but you know that what is y minus x? Y minus x should be greater than r, right? Because you assume that this has a lower value than f0x, right? Then it cannot be in this neighborhood. Neighborhood of the definition associated with the lower minimum, right? If this is in the neighborhood, then this of course has to take a value greater than r. So we know that now norm of x minus y, the distance between x and y has to be greater than r. So if you plug that here, you can see that the value of theta should be between 0 and 1 by 2. Okay. Now, yeah, of course, Z is a convex combination between x and y, so Z is feasible. We know that. Now, what is the distance between Z and x? What is the distance between Z and x? You can verify that here. Z minus x, you take the norm. Replace Z with a convex combination of x and y. Okay, so you get this guy. Now you put the value, substitute the value of theta, this value. Okay, so this norms will get cancelled and you will get r by 2. R by 2. Okay, so why I am just making a particular choice of theta such that I want to say that I can find an Z in this region. Okay, now the distance of Z from x is r by 2, which is less than r. That means Z is falling within this neighborhood. Okay. Now you use the Jensen's inequality, where you evaluate f at the point z, which is theta y plus 1 minus theta y, which is given by the inequality. So then we can plug in an inequality here and say that this is less than f0x, because we consider here f0x and f0y, right? So any point between this will be less than f0x. That's what any value between this point will be. You are drawing a line here, and any value will be less than f0x maximum. Okay, so I'm just plugging in that. So this says f0z is less than f0x, but our earlier assumption was f0z is greater than f0x, which contradicts our assumption. Then we can say that it is not possible to have this scenario, like the moment you pick, you find an local optimal point. Now you cannot assume another point which is which has lesser value, lesser function value than that.
Greater function.
Lesser function value. If it's greater, then there is no problem. F0y is less than F0x. F0x, I assume that I found an x such that like find an x which is a local minima. Okay, so if you find a local minima for a convex function, then you cannot find another point which is taking value less than that, provided that the constraint sets are feasible. So this is the point where we say that if you have a problem where the objective function is convex and the constraint sets from a or the feasible region is convex, then the problem is called convex. And this is very important because uh, any local minima indicates the global minima. Any local minima will be a global minima. Okay. Yeah. Now we you can read the proof. Now I think you have the idea. Now you can easily understand. Now. Now you see that if the function, objective function is differentiable, there is an optimality criteria for differentiable objective. Of course, this criteria you cannot apply for a function which is not differentiable. Okay, there can be a converse problem where the associated function can be non-differentiable function. Okay, but if the function is differentiable, you can use this formula, which says that x is optimal. So we have a function of 0. X is optimal if the moment you say x is optimal, x is feasible, right? X has to be feasible. And for any other feasible y, if you draw a line, that is, if you take this quantity y minus x and take the inner product between that and the gradient evaluated at this optimal point x, that will be positive. Okay, so I will we are not doing the proof here, but you can read that from the text. But I will give you an intuition here. So let's say I have a function. These are the level curves or contour of the function. That means the minimum point will be here. As you move further, the function value increases. You got it, right? So now I want to minimize this function. So if the function is unconstrained, that means there is no constraint here. What will be the minimum value? It will find this point as the minimum. I mean this point, right? The x corresponding to this point will be the optimal point, and the value associated with this point will be the optimal value or minimum value. Now I add this constraint set. So this is a set which is coming from our constraints. Okay. Now if you minimize this, what will happen? The solver will try to find a point x with a minimum value. So the solver will try to move to this direction, but that has to fall within this set, right? So then which will be the optimum point? That will be this, where it just touches. And if you move towards this direction, that it will leave from this feasible region, right? So it is a point where it just leave the feasible region. It's about to leave the feasible region, you can say that. So this will be the optimal point. Now if you draw, you have a function here. If you draw the gradient at that function, it will be normal, right, to this hyperplane, right? So that will be normal. So what I'm saying here is, if you take the inner product between that and any feasible region y here, so here this is my y from here, okay? So x I am considering as x opt. Sorry, I am using a different notation, and for this I use x, okay, here. So this is the optimal point. and any feasible point I'm considering as x here. So what our original condition for optimality says that if the function is convex and the sets are convex, then this gradient, uh, if I take the product between inner product between these and this vector, that is x minus x opt, okay, sorry, x opt, yeah, x minus x opt, that will be positive, right? That means this angle has to be less than 90, because cos of that has to be less than 90. So yeah, so that's the beauty of this. But what happens if you take a non-convex function? So here is an example. So the optimum value is here, okay, and so let's say this is the tangent here, and the gradient points to this direction, and for all feasible region this is not true. For example, if you pick a point from x here, you can find this line making an angle greater than 90 here. So this is not happening in happening if the set is not convex. So that's what these optimal conditions maybe geographic, graphically meaning. Yes.
Like,
Yeah.
here y is any set, any point inside a convex set, right?
Yes, any point.
So it depends on the angle depends on the
Yeah,
point.
if you pick a point here, the angle is less than 90. But the point is, if it's a convex, if you pick any point,
Okay.
the angle will be less than 90. But here, this need not be true.
Yes.
Okay, that's why I wrote theta can be greater than 90. It not must be. Okay. So basically, what we are saying is this condition does not hold always for convex set, non-convex set here.
But if the set is half space, like,
Set is half space, then it is convex.
but the angle will be like 180, right? If you take and subtract.
Set is
Yeah,
half
it will be
space
90.
means
Yeah, it will be 90.
set is half space means
Okay.
this is the region. So if you take it will be, yeah. Also you can see that. So if you slightly rearrange this, this forms an equation of half space in Y, right? So here you have this, and the gradient delta F was pointing to this direction. This is the minus gradient. So what you are saying is, you are indicating using this equation, you are pointing to these half spaces. Or in other ways, you can say that this gradient evaluated at the optimal point define a supporting hyperplane. This we learned what is a supporting hyperplane. It is just like touching that stone. So this point defines a supporting hyperplane. Yeah. So let's move on. You can see the proof from the book if you are interested. Now let's consider some cases of this. One is unconstrained problem. Yeah. So one interesting thing is, okay, I said this, okay, but from your maybe high schools you learn that, okay, the function at minima, okay, optimal point is a minimum point. So we say x is optimal to the problem. That means for the problem, x is a minimum. If you are minimizing, it's a minimum point, right? So, but from the high school, we saw that if a point minimizes the function, right? At that point, the gradient has to be zero, or derivative has to be zero, right? So then what's the meaning of this? So what, then this has to be zero always, right? Yeah. So what? So what I'm saying is, if the gradient is zero, what is the meaning of this inequality, right? So the point is, there we were not considering any constraints, okay? That is important. So for example, you have a function like this, unconstrained problem. You are asked to minimize this. So the minimum point will be here, and the tangent will be having a zero slope here, okay? But now the problem is this is for a constraint problem. You are putting a constraint here. So that means you are saying that, okay, I put a constraint. I have to minimize over this region. Oh, I have to minimize over this region. Okay. In that case, what will be the minimum point of the problem? It will be this guy, not this guy. It is this point. At this point, the gradient is not zero. Okay. So the moment you put constraint, the problem can
Problem change
how
with
to
respect to
how to
constraint.
minimize from a region, from a feasible region. So it forces it. So that point gradient need not be zero. That's the point. Yeah. So now we move to different category of this optimality condition. One is unconstrained problem, which we just saw here. The first problem with the all domain. Yeah. So if the problem is unconstrained, what happens is we know that if the problem is unconstrained, the gradient will be zero. Okay. It's unconstrained, so that means it will be zero. So how do you prove that? So this is the original optimality condition we have. Now the problem is unconstrained. So now instead of here we said for all feasible y, now we don't have the concept of feasibility since the problem is unconstrained. I can pick y from any point in Rn, right? So I pick, for example, I pick a y minus x. So I can pick y. So that essentially means I can form, I can come up with a y minus x. Let's say I take an example minus, my y minus x is minus gradient. Okay, just plug that here. So that means you have gradient transverse into minus of that, which is minus of norm of the gradient square, which we are saying is greater than zero. This is possible only if this guy is zero. Yeah, so that way we can prove this, or we already know this from high school, right? That gradient or derivative has to be zero. Now, equality constraint problem. This means you only have an equality constraint. Minimize f zero subject to x equal to b. In that case, yeah, so let's consider an optimal point x and another feasible point y. So this is our original optimality condition, right? So now, since y is feasible, I can write ay equal to b, right? This is the uh, constraint, right? And x is feasible, I can write x equal to b. That means I can write a into, if you subtract this, a into y minus x equal to 0. That means y minus x belongs to the null space of a. Okay. So here I would ask you to revise the linear algebra concepts like column space, row space, null space, etc. Okay. It's not possible to teach that here. So this is a prerequisite. Yeah. So y minus x has to belongs to the null space of A. Means if you pick any element from null space of A and multiply with A, that has to give 0. And yeah, so where was I? Yeah, so then you can write the inner product between this and a vector from null space of A has to be greater than or equal to 0. This will happen only if so if V belongs to null space of A, then we can also say that minus V also belongs to null space of A. Because you multiply something with x, that gives 0. So then that's the case with minus x. So then you can also write that delta f0 x transpose V minus V greater than or equal to 0. So this implies this quantity implies that this has to be equal to 0. So you are multiplying a vector with another vector, which is giving positive or equal to 0 value. And then you are doing the same multiplication with negative of the second vector. Again, you are getting positive or 0 value. This can happen only if that inner product is 0. That means these two guys are orthogonal. Now, if you say, again, you have to take some concept from linear algebra. If you say that this gradient is orthogonal to the null space of A, then you can say that this gradient belongs to the range space of A transpose. Okay, so we are using a result. This you have to revise by yourself. Yeah, basically, if this is orthogonal to null space of A, then we can say that this is an element from the range space of A transpose. That means I can write delta of 0x as some A transpose into some vector B or minus B here. Okay, take this to this side and we can write that like this. Okay, so this is what, if that is an inequality constraint, there exists a V such that we can write this form. Okay, so this we are just don't worry, we are just making a statement here about this equality constraint. But later, during you'll see in Lagrange multiplier, you'll see this in detail. Okay, this condition. Okay. When you learn this, you will revisit this and study this in later. Okay. Now there is another concept, another special category where we are minimizing our non-negative orthent. That means minimize x. Only constraint is x has to be greater than or equal to 0. So by now you should be able to tell what is this inequality. If you say, you are saying that a vector is greater than or equal to 0, that means component wise, it's each components are positive. So then in that case, what you are saying is, okay, let's take the original optimality condition, and x and y are feasible. That means x and y are positive or 0. And now, so any value of y, this should be satisfied. So I just plug in 0 here. So then delta, the gradient transpose into minus x has to be greater than 0. Or in other ways, gradient transpose into x has to be less than or equal to 0. Remember, x is the optimal point. Now, next is, so what I'm saying is, I have a vector A and a vector y minus x. If I do the inner product, that has to be always 0. So, and the second vector is a positive vector, right? This, no, it need not be positive. Yeah. So what I'm saying is, yeah, what I'm saying is, for example, if you consider delta f to be -2, 1, 1, okay, I can pick this y, I can find a y minus x such that if you take the inner product between this guy transpose into inner product between, for example, I consider this as 1, 0, 0, okay, this will be less than or equal to 0, right? This is less than 0, right? So this for this condition to hold, this has to be positive. Okay. Now, if you compare 1 and 2, what you are saying is, okay, you have an inner product which is
just like the matrix is, I think it should be like -2 in row wise.
Yeah, that's why I wrote the transpose here. This means this is equal to -2, 1, 1, right?
But can you multiply 3 cross 1 matrix to 3 cross?
This is not 3 cross 1. This is 1 cross 3. I put a transpose of that.
Okay, after you have to do transpose. So then it will
see, this is a 3 cross 1 matrix, and I put a transpose here. So that means it's a 1 cross 3 matrix. So I already wrote this. Then I don't want to wrap. Then I just put a transpose. But this is correct. Yeah. So yeah. So if you consider this, what I'm saying is you are multiplying we are taking inner product between 2, and the second, this is positive, right? That's the non, we are optimizing our non-negative ortho. This is positive or 0, and this is also non-negative. This can happen only if the individual elements are 0. So you are multiplying two positive vector and saying that the result is less than or equal to 0. This can happen only if the individual components are 0. So take this here, right? So then this gives rise to two cases. One, if x is greater than 0, the gradient has to be 0. If x equal to 0, the gradient can be greater than or equal to 0. So this is happening when you are minimizing our non-negative ortho, and this is an important case, which is called complementarity, that you will learn later. Okay, but as of now we are just mentioning this. Yeah, now equivalent convex problem, next topic. So we already saw one case of this. We in the standard form, yeah, here we saw. So this problem is equivalent to this problem. Okay, that means when do you say that a problem is equivalent? It's not identical. Identical means it has to be the same problem. So this is equivalent. So informally we can say that if the, so we have a problem which is a bit difficult to solve, but you found another problem which gives the exact solution. Okay, so if you solve this, you will get the other one, but it's not the same problem. In that case, these are equivalent problems. That's all. This is an informal way of saying things, but this is enough. Yeah, so some example. So now what we are seeing is you have a problem. Can we come up with an equivalent problem in a different format? Yeah, so take this standard form: objective, inequality constraints, linear equality constraints, and this is equivalent to I am here eliminating the equality constraints. So I form a new problem. So I will say what it is. So now instead of x, I use a different variable, f, a matrix f into z plus x0. Okay, and now the minimization is not with respect to x, it is over z, this variable. Okay, now the point is, how do you pick x0 and f, right? You don't know that. So one way to do this is pick x0, choose any particular solution of this ax equal to b. That is, ax0 should be b. So pick any such x0. Okay, you have that. Now f has to be again linear algebra. Columns of f span null space of a. That means so you have f here. So these are the columns of f, c1, c2. These are vectors. Okay, column vectors. So and then you are multiplying that with the z, fz. So what you are having is this vector. Okay, so that should be in null space of a. If you multiply this with a, that should give 0. Okay, you can read this later, even if you have some doubt, because this needs the background from linear algebra. Okay. Anyway, in essential, in conclusion, what we are saying is, so here we have f, right? So if I take ax, this will be a into fz plus a into x0, right? And this guy has to be 0, and this should be b. Okay. So then this is like a
X equal to
yeah. So this will be right. Then you can replace x with this two case. So this is an equivalent problem where we eliminate the equality constraint. So next is the reverse. We are introducing the equality constraint. So we have a problem of this form. Okay, a0 x plus b 0 ax plus b. Now what I do is I introduce a new variable y. Okay, and just replace y with ax. So this is a new equality constraint. So this looks funny, right? So we didn't do anything, just equate this guy to a variable and put that in the constraint. Okay, but this kind of things are small tricks are very useful. Some you will see later in the course. Okay. Yeah. So here, the point is just introduce a variable here. So the thing is here we introduced an extra variable x y here. Okay. So now the minimization is with respect to x and y. Although x is not part of the objective function, it plays a role in the constraint set. Okay. Yeah. So like this may look crazy or some simple, but this kind of techniques are useful later. You will see that. Now a simple thing, introducing a slack variable. Yeah, we have 5 more minutes. I think we can finish this. Introducing a slack variable. So I have a function like this. So what I do is replacing this inequality with an equality here. So what I'm saying is this left side is less than or equal to right side. So instead of that, I add a positive quantity here, Si, and I say that it is equal to Bi. That's all. It's a lazy way of doing it. Like just put an Si here, right? And this is true, right? So you are saying like 2 is less than or equal to 3. Then I can find a positive quantity, add with 2 and say that this is equal to 3. So these are some simple way to rewrite the problems, but some of this is very helpful. Some of them are very helpful, which you will be using later. Now next is epigraph form. This is again a very simple thing. So you have a function. So let's take the standard function where you are minimizing f0x over some constraints, like inequality and equality constraints. So now I replace that with a linear constraint, linear objective function t, and saying that f0x is less than or equal to t. I am putting this. I am adding this new constraint, which means that initially your problem was to minimize this in x. Okay. Now I am introducing a different variable t, and what I'm saying that okay, you try to minimize this t value of t, but that should be above f0x. So what will happen at the end? You find t and you are picking minimum t, which is above the original function. So that will be this point, right? Right. So you are finding the values of t, which minimizes this, but it should not go below the function. So that will pick the optimum value. So now the new optimization problem is in variable t and x. So now you are searching over all the xt, and now finally you will find this x opt and t opt optimum point from there you can pick the x opt. Okay. Yeah. So the beauty of this is sometimes this function can be not sometimes this function can be non-linear. Okay, convex but non-linear. But now if you rewrite this, now your objective function is just t. It's a linear function, right? So this can help in some cases. Yeah. So that's why we call this as epigraph. This is why we have this. This is forming something similar to epigraph. That's why we are forming this as calling this as a epigraph. Another thing is you have an objective function. So to minimize, but we are minimizing our sum of the variable. So here, the objective function is a function of x1 and x2, but here I have a constraint only in x1. Okay, in that case, what I do is okay. Now I just minimize this function first with respect to x2. Okay, so I form a new objective function f tilde, which is minimum or infimum of the original function over x2. Okay, now I got a new L tilde. Now just use that. Now you have everything, you have a new problem with only in x1. Okay, so this is useful. For example, you have a function, you have a differentiable function in x2, let's say, yeah, x2. So now you got a problem where you saw that this is a complicated function, but the constraint set is constraint is only applicable to x1. Okay, so now you can take the function and find the minimum value if this is differentiable with respect to x2, and find the minimum expression and then plug that here and continue with just export. So these are some small tricks. Yeah, I think we can stop here. Maybe just mentioning a few points here. Quasi-convex optimization. It's same as the same standard form. Only difference is F0x is now quasi-convex. Okay. Other things are same. This has to be Fi has to be convex. Okay, convex, not quasi-convex. Convex, and this is linear. And yeah, as we said, for this, does a local optima need not be a global optima. At this point, this is a local optima. This need not be a global optima. Okay, we'll stop here.